Hello, the main objective of the present lab is to study the falling motion of an object that is dropped from rest, integrating theory, experiment and computational modeling. I captured a video of a crumpled paper ball that was dropped from rest and analyzed the video using Tracker. I constructed two computational models for predicting the motion. Subsequently, I compared the predictions of the computational models to the observations by plotting both the observed and the predicted positions versus time on the same graph. According to the results of this lab, the first model, which includes only the effect of gravity, predicts with reduced accuracy the falling motion of the crumpled paper. The second model, which includes both the effect of gravity and the effect of drag, predicts well the falling motion of the paper. Based on Newton's second law, we can predict the final velocity of an object and subsequently the final displacement of that object. Near the center of the Earth, the weight of an object equals to the mass of the object times g. The direction of the weight is the same as the direction of g and toward the center of the Earth. When an object moves in the air exerts a restraining force on that object, which is called air resistance or drag force. The drag force depends on the speed of the moving object, on the cross-sectional area of the object, on the shape of the object, and on the density of the air. According to the above, the formula for the drag force is the one shown. The factor B incorporates the dependence to the mentioned factors of the cross-sectional area, the shape, and the density of the air. The direction of the drag force is always opposite to the direction of the motion, so the unit vector of the drag force is opposite to the unit vector of the object velocity. At time t equal to 0 second, an object of mass m is dropped from rest from a height h above the floor. The forces acting on the crumpled paper during its fall are the weight and the drag force. The net force acting is the outcome of these. The computational model. I specified a coordinate system with a positive y-axis pointing upwards. I calculated the mass of the crumpled paper and I set its initial position at the beginning of the coordinate system. I also set g equals 9.8, b equals 0 for the first model, and b equals 0.00224 for the second model in order to the final predicted position coincides with the observed one. The models are based on the Newton's second law of motion, and I used the shown expressions for the weight and for the drag force. I represented the weight and the drag force with arrows. The tail of the arrows was set at the position of the crumpled paper. The direction of the arrows was set the same as the direction of the forces they represent. The arrow scale was chosen so that the magnitude of the weight be twice the arrow scale. Finally, we have the showed assignments. Here is the first computational model. The drag force is equal to 0. Here is the second computational model. The drag force exists and is opposing to the motion. I compared the predictions of the computational model to the observations by plotting both the observed and the predicted positions versus time on the same graph. As you can see, the model, which includes only the effect of gravity, predicts with reduced accuracy the falling motion of the crumpled paper. As the speed of the paper increases, the model's predictions deteriorates. The second model, which includes both the effect of gravity and the effect of drag, predicts well the falling motion of the paper. Applying Newton's second law, we can find the actual displacement of the crumpled paper. In the first model, the predicted displacement does not depend on the drag force. The difference between the observed and the predicted displacement is proportional to the real drag force acting on the crumpled paper. In model 2, the predicted displacement depends on the drag force, and the difference between the observed and the predicted displacement is proportional to the difference between the actually existed drag force and the drag force calculated by the model. The more correct the formula of the drag force we used in the second model, the less the difference between the observed and the predicted position. If the formula was calculating perfectly the real drag force, the difference would be zero. Actually, the formula we used gives a close estimate of the real drag force, yet not perfect, and this is the reason for the slight difference between the observed and the predicted position. Thank you for your attention.